There's been a lot of talk about quantum computers lately, and them being the future of computing as a whole. But with all this talk, understanding how and why they are important has become a need. The rest of this video will focus on explaining the fundamental building blocks of quantum computers, specifically what a qubit is, a quantum gate, and a quantum algorithm. First, let's start with a qubit. A normal computer, cell phone, or any other electronic device uses something called a bit. This bit is essentially a 1 or a 0. You can also think of it as a true and a false. Data on a very base level on all computer systems are saved in these bits, 1 or 0. This language of 1 and zeros is called binary. These 1s and zeros are made specifically by sending an electrical pulse that is either current or no current. So basically an on and off state, 1 or 0, or true and false. But quantum computers don't use bits, they use something called a qubit, which is short version for quantum bit. The reason qubits are special is because they can be a 1, 0, or 1 and 0 at the same time. When they are in the state of 1 and 0 at the same time, it's called superposition. The superposition state actually leads to an exponential growth in the data that can be used. And it's usually denoted as 2 to the power of n. N is equal to the amount of regular bits you'd have, and you're turning them into what would say a quantum. One of the ways scientists show how big of a growth it is by just comparing 30 bytes. 30 bytes in the regular world, where most people use, is nothing. An average song someone would download is around 3 to 4 megabytes, which would be around 8 million bits. You can see then how little 300 bits would be. But 300 qubits in the size comparison would be 2 to the power of 300, which is larger than the amount of atoms in the entire universe. Now that you know about qubits, we'll go into quantum gates. Classical computers use something called logic gates, which take an input and usually output a single bit. An example of a regular logic gate is the NOT gate, which takes 2 bits and outputs a 1-bit reading by reading what current state the bit is in. It'll output true if it's in the state you want and false if it's in the state otherwise, and or 1 and 0, because in computers, true and false are usually the same as 1 and 0. While the classical NOT gate is very helpful in making computers faster and easier to work with, there is an equivalent NOT gate in quantum gates, but again, it kind of acts the same as a regular one. So the best example of an actual quantum gate would be the Hadamard gate takes a number of qubits and then obtains a number of superposition that represents all possible combination of those qubits. This just means it takes in a bunch of qubits, it puts them in a superposition, and then it gives you this formula of a bunch of different states that they can be in, every possible state they can be in. This makes it a lot easier to process a lot of data very quickly, which shows how it beats a classical computer. Now that we've gone over quantum gates and qubits, the last one to really understand a quantum computer is a quantum algorithm. A basic algorithm is just a set of instructions that is used to get a result. The time it takes to finish any certain algorithm can drastically change depending on the algorithm. An example I'm going to use is the factorization of integer numbers. Again, you don't need to know what it does, just know that it's very slow. The specific formula we have for the time it takes, the formula I'll put up screen right now. This one right here, if you plug in all the values, you get the time it takes for a classical computer to complete this algorithm, the factorization of integer numbers. And it is very slow. But if you have the same algorithm written for a quantum computer, it has this formula instead. As you can see, without doing any math, it's already a lot less. It's not an exponent, which instantly makes it smaller, as well as it's not 2 different logs times each other. It's just 1 log. And again, this comes out to being a lot faster. Lastly, I'll talk about the different materials. Since the start of quantum computing, many different materials have been tested in making a qubit. The different materials that are kind of the most popular so far are ultra-cold atoms, photons, superconductors, and molecular systems. The biggest problem with a fair number of these qubits is the difficulty in entangling them. And if entangle them, it makes the quantum computer basically a regular computer with a lot more steps. And it is a key component in making quantum gates, as we talked about before with the Hardman gate. Specifically, the use of molecular materials. Molecular just referring to molecule. Some examples of a couple molecules would be like H2O, water, CO2, and a lot more. It's just a mixture of atoms together, bonded. But specifically, quantum materials have been a lot better because they give a lot more control, specifically chemical control, making it easier for the scientists to control the computer as well as quantum entangle the particles themselves. Really, in conclusion, the world of quantum computers is an ever-changing field that will be the future of computing, not probably at-home desktop computing, just because of the ins and outs of how quantum computer works and how it wouldn't be faster for certain things. But specifically, out of all of the different materials tested, molecular materials have shown the most promise so far.